Now the next topic is flow over the parallel flat plate with the constant heat flux conditions. So till now we were discussing isothermal conditions, and now we will discuss constant heat flux condition. So the plate may be isothermal. So in that case, the temperature of the entire plate would remain constant at Ts, for example. Over here we are considering that the flat plate is at constant heat flux. So in this case, when the heat flux is constant, so the temperature of the surface or the temperature of the wall may not be uniform throughout, right? It may not be uniform throughout, so it will vary from location to location. However, the heat rate would remain constant, because the per unit area would remain constant, because the heat flux will remain constant. So it may be isothermal condition, or it may be constant heat flux condition. If we consider the wall at the same temperature, means if we consider isothermal wall, so then the temperature of the surface would remain the same throughout. However, the heat flux would then be different. And if we consider the constant heat flux condition, then the temperature at various locations would be different. So if the flow is taking place, and if it is laminar flow, then the Nusselt number is found out. Local Nusselt number is found out using this expression, which says 0.453 Reynolds half Prandtl 1/3. And for turbulent flow, local Nusselt number is given as 0.0308 Reynolds 4 to the power 4 by 5 and Prandtl to the power 1 by 3. And over here we can find out the average Nusselt number using this expression, 0.68 Reynolds half Prandtl 1/3 for laminar flow. Over here we have this expression for average temperature. Ts minus T infinity bar is equal to Q double dash times the length over K times Nusselt number. This is not a difficult expression at all. In fact, you can write it yourself using Q is equal to HA delta T. So if you start with Q is equal to HA delta T, and then you write delta T on one side, so it would be Q over HA. So we have this heat flux over here, and then Q by A can then be written as heat flux Q double dash, which we see over here, right? And we would also have the Nusselt number in the denominator. So if we use Nusselt number is equal to HL over K expression, so using that particular expression we can then write H as in the form of, in terms of Nusselt number and K and L. So this is a very easy expression which you can write yourself using Q is equal to HA delta T, and then writing H as H in terms of Nusselt number, using Nusselt number is equal to HL over K expression. So these are 5 typical points, but these are not some sort of universal points for the convection calculation. It says we need to focus upon the flow geometry, whether the flow is taking place over a flat plate or over a cylinder or over a sphere, right? And then we need to specify the appropriate reference temperature and evaluate the fluid properties at that temperature. So we will see in a bit, when we would be solving the problems, that we need to calculate or we need to refer to the tables to find out the fluid properties, and we need to calculate the fluid properties at a reference temperature. And there are various ways in which that reference temperature is found out. We will discuss them when we will reach to that point. In some cases it is taken as the average temperature of the surface and the T infinity, and if it is if it is the flow taking place through a pipe, and if it is, for example, a constant heat flux condition, so then of course the temperatures would be different at inlet and outlet. So in that case we usually take the average of the bulk temperature of the fluid at inlet and outlet. So we will see when we will reach to that point. So over here point number 2 means means that we need to calculate the fluid properties such as Prandtl number, such as diffusivity, such as conductivity, because all those properties would be required. All those properties would be required in the calculation of Reynolds number and Prandtl number, which will be used in the calculation of Nusselt number, because we have seen at various points in the previous slides that we have the expressions of Nusselt number in terms of Reynolds number and Prandtl number, right? So we would be calculating the fluid properties at that particular reference temperature, and then we would be calculating the Reynolds number, and we would be looking at the Prandtl number from the table, and then we need to decide whether a local or a surface average coefficient is required. And then this is the most important point, as I was discussing earlier as well, that we need to select the appropriate correlation. This is very important, and this is in fact the main thing, right? As I was mentioning earlier, that we do not need to remember all those expressions of Nusselt number by heart. Of course we cannot. So all we need to do, so we would have the table available with us. All we need to do is to select the appropriate correlation as per the geometry, for example flat plate or cylinder or sphere, or as per the the type of flow, means laminar flow or turbulent flow, or whether it is the unheated starting length problem or a simple problem. So we need to be very careful while we are selecting the appropriate correlation from that list of various correlation expressions. We will look at that list in a bit towards the end of this chapter. Now the cylinder and cross flow. So now over here we would be considering the flow over the cylinder. So in this particular topic, when the flow is taking place over the cylinder, first of all the critical Reynolds number is 2 exponent 5, which was 5 exponent 5 in the case of flat plate. So that value of critical Reynolds number, which is 2 exponent 5, would mean that the boundary layer would remain laminar if the Reynolds number is less than this value. The boundary layer would of course remain laminar if the Reynolds number is less than this critical value of 2 exponent 5, and if the Reynolds number exceeds this value of 2 exponent 5, then it would become turbulent flow, right? It is for the flow across a cylinder, right? Kindly note that this value of critical Reynolds number is 2 exponent 5 for the flow across a circular cylinder. Over here we can see that the flow is taking place over this cylindrical surface, and while the flow is having a velocity of v, and while it approaches the surface we would consider its velocity as u infinity. So when the flow will try to go past the half of the cylinder onto the other half of it, so we can see that some sort of separation, which we call boundary layer separation, takes place. So this separation process will take place when the fluid will flow over the cylinder, over any cylindrical object, uh, because the thing is that the streamlines would not be able to follow this curvature on the other half, this curvature on the other half. So due to this, since they will not be able to exactly follow this path, since they will not be able to exactly follow this circular path, so rather the streamlines would come in, the flow would come in, and then instead of coming over here, it will try to go in this particular direction. It will try to it will try to it will try to go in this particular direction, right, as is illustrated over here. So since the fluid will not be able to completely follow this circular path of the cylinder, of the other half of the cylinder, so therefore it would give rise to a wake region. Wake means some sort of empty region, you can say. So there would be a wake region on the other side of the cylinder, which would give rise to a to boundary layer separation phenomena, which we will be discussing in the upcoming slides. So as you can see over here that it says that at very low upstream velocities, upstream means the velocity before the cylinder, such as here, and this would be considered as downstream location. So if the upstream velocities are very low, or if, giving rise to very low values of Reynolds number, such as less than 1, so then the fluid will completely wrap around the cylinder, and the two arms of the fluid will meet on the rear side of the cylinder in a very orderly manner. Right? So if the Reynolds number is very small, means if the velocities are very low, so then this separation phenomena and all that will not take place. Rather the fluid will, the two arms means this arm and this arm, they will follow this curvature, and then they will meet over here, and the flow would be very orderly downstream as it was upstream, but at higher velocities. Over here we were discussing about very low upstream velocities. Over here we are discussing now the very high velocities. So the fluid will stick to the cylinder on the frontal side. The fluid will stick to the cylinder on the frontal side. Frontal side means this half of the cylinder. So the fluid will stick to this half, to the frontal side, but it is too fast to remain attached to the surface as it approaches the top of the cylinder. Hence what will happen is that the boundary layer would detach. The boundary layer would get detached from the surface, would get separated from the surface, thus forming a region, a separation region behind the cylinder. So over there we call this region as the wake region, which is characterized by vortex formation, right, because of the higher fluid velocities. So the flow would be chaotic over here in this region, which is a characteristic of turbulent or highly turbulent flows. Now when the fluid is flowing over that cylinder, and so what happens is that due to the separation of the boundary layer, due to the separation of the flow from the cylinder surface, the flow reversal takes place. Means if you took a look at the boundary, at the velocity profile, you will see that at a particular point the velocity would not be having this particular profile. Rather you can say that this particular profile starts from here, right, from this point onwards, and this would be the point of separation. So a little further downstream, what will happen is that due to the formation of vortices in this wake region, so due to the formation of vortices, the flow reversal will also take place. And due to the flow reversal, I think flow reversal is a self-understood term, right? So, and due to this flow reversal process, the boundary layer would then be made in the opposite direction, right? And then it will attain its original shape, right? Its original shape. So in this region, the majority of the velocities would be in this direction. However, over here, due to the formation of vortices, a process of flow reversal will take place. Over here we can see that the separation is taking place at two different angles if the depending upon the type of the boundary layer, whether the boundary layer is laminar or whether the boundary layer is turbulent. So if the Reynolds number is less than 2 exponent 5, means if the flow is taking place over the cylindrical surface crosswise, and if Reynolds number is less than 2 exponent 5, so then the flow would be classified as, the boundary layer would be classified as laminar. So the boundary layer would remain laminar and the separation occurs at about 80 degrees. So over here this angle is about 80 degrees, and then the separation phenomena would start. However, if the flow is turbulent, if Reynolds number is greater than 2 exponent 5, so then the boundary layer transition would occur, and of course the flow would at one time become turbulent. So we can see over here that over here we have got, means in the upstream region we have got laminar boundary layer, and then there is a transition taking place, and then the boundary layer would become turbulent. So if this is the case, then the separation is delayed to about 140 degrees, and this angle of 140 degrees is shown over here in the figure. It is figure 7.8 of our book in Cropper and Leavitt. So if the flow is turbulent, the boundary layer separation process gets delayed. Right? You can call it in this manner, that if the flow is turbulent, then the boundary layer separation process would get delayed. Now this graph is between the drag and the Reynolds number. So on the x-axis we have got the Reynolds number Re, and on the y-axis we have got Cd, which is the coefficient of drag, and it is for the cross flow over a smooth cylindrical surface and a smooth sphere, as has been mentioned over here. Now in this graph, what we can see is the effect of increasing Reynolds number on the flow. Right? So if we see for very low values of Reynolds number, such as in this region where it is less than even 1, because 10 to the power 0 would mean 1. So in this particular region the flow would be very creeping sort of flow, and we can see that the drag coefficient decreases, it goes down with an increase in the Reynolds number. Right, so there would not be any flow separation in this regime, as we had seen in one of the previous slides, that if Reynolds number is less than 1, then the flow will remain stuck to the cylinder for the first half, and even on the second half of the cylinder as well. Now in this particular region where it is beyond 1 and it is around 10 or so, where the Reynolds number is 10, so the separation would start occurring. Separation would then start occurring on the what you can say the other half, the downstream half, or the rear side, right? So this is what will happen, and if we go further down on the Reynolds number on the x-axis, and so we can see that in this particular range we can see that the curve of CD of the drag is more or less is not really on a decline. So we may consider it as relatively constant. Right, so the coefficient of drag is relatively constant in this particular region where Reynolds number varies from 1000 to about 1 exponent 5. In this region the boundary layer would still be laminar. The reason is that the critical value of the Reynolds number is 2 exponent 5 is 2 exponent 5 for as mentioned on one of the previous slides. It was 2 exponent 5, so it would remain the boundary layer would remain laminar, but the flow in the downstream region means this region, right? This is the downstream region and this is the upstream region. So the flow in the downstream region would be turbulent, right? So that would be turbulent. And of course turbulent means, so if it is turbulent, so that would give rise to a wake region and flow reversal and all that. And then we see in this particular region where it is between 10 to the power 5 and 1 exponent 5 and 1 exponent 6, we see a sudden drop in the drag. So this sudden drop would be due to the reason that the boundary layer would become turbulent, because it would be more than 2 exponent 5, and because it is greater than exponent 5, 1 exponent 5 or 2 exponent 5, and it is reaching 1 exponent 6. So it would surpass it would cross the critical value of the Reynolds number, so the boundary layer would become turbulent. So therefore we would see this sudden drop in the drag. Okay, so this is how the flow over the cylinder would take place with an increasing value of the Reynolds number, means when the flow would change from laminar to turbulent. Now let's take a look at some of the expressions of Nusselt number while considering the heat transfer over the cylinders for cross flow over the cylinders. We can use this particular equation of Nusselt number 1.15 Reynolds raised to the power half Prandtl 1/3. However, this expression can also be made use of. That average Nusselt number is C Reynolds to the power m Prandtl to the power 1/3 for Prandtl number greater than 1.7, and all for most of the times we would be having Prandtl number greater than 0.7 unless if it is some flow of liquid metal. Otherwise, for any gas or for any other oil or for any other heat transfer fluid, Prandtl number would be greater than 0.7. Now in this particular equation there are two unknowns that you can see over here, C and M. We have got C as an unknown and M as unknown, right? C and M. So this table, which is table 7-2 of our book, will be used to find out the values of C and M, and that would depend upon the value of Reynolds number. So we would be calculating the Reynolds number, and accordingly we will select the value of C and M, and we would be able to get the value of Nusselt number from here, from this expression, and then of course we would be equating it to HD over K to get the value of H, heat transfer coefficient. This equation means this equation, which is written over here in terms of C and M, can also be used for flow over cylinders of non-circular cross section. So for non-circular cross section we need to refer to table, for non-circular cross section we need to refer to table 7-3 of our book with characteristic length D and the constant obtained from table 7-3. So let's take a look at 7-3 as well. In table 7-3 of our book, these are the values of C and M. First of all, let's take a look at the title. It says constants of equation 752, means the previous one that we were looking at the last page. for non-circular cylinders, right? It may be a duct of a rectangular cross section or hexagonal cross section or a square cross section, and in the cross flow of a gas. So it may be this geometry or a hexagonal geometry, right? So there are various types of geometries, commonly used geometries, that are given over here, and we would be selecting the value of C and M for this particular geometry by calculating the Reynolds number, and we would be putting the D as this length. In this case, the D would be this height, and in the case of a square, it would be D would be this height. Similarly, so D would not really be the dia, but the value of D would be selected in this particular manner. Now there is another correlation for finding out the Nusselt number, and which is given over here. In this particular expression, the properties are evaluated at the film temperature. So film temperature is the mean temperature of Ts and T infinity, and all the properties are evaluated at T infinity. Sorry, it would be T infinity except Prandtl number, which is evaluated at Ts. So the equation is of this form: C Reynolds to the power m, Prandtl to the power n, Prandtl number over Prandtl number at the surface to the power 1 by 4. Then kindly correct this thing, that in this particular expression which is written over here, this one, the one on the top, so the properties are evaluated at T infinity. Except Prandtl number S, which is evaluated at Ts and not T infinity, at the surface temperature Ts. Now another expression for Nusselt number is given over here. Of course, it's even lengthier than this one, but you will find that all the expressions that we are looking at have got Reynolds number in them and Prandtl number in them. So they all are functions of Reynolds and Prandtl numbers, and it was proposed by Churchill and Bernstein, and all the properties are evaluated at TF, means at the film temperature. Film temperature is in fact the average of Ts and T infinity. So TF is equal to Ts plus T infinity over 2. Film temperature is the mean of the Ts and T infinity. Okay. So there are various equations besides those equations that we are looking at, and we are approaching very near to the case where we would be looking at the table where we have got all those expressions listed for all the three types of figures, means flat plate, cylinder and a sphere. This is for the sphere. Nusselt number is given as per this expression, and Nusselt number can also be given as per this expression. So at the end, let's take a look at this table, which is 7.7 of the 7th edition of in Cropper and Dewitt. As the title says, summary of convection heat transfer coefficient relations for external flow, right? So it is for external flow because we have internal flow in chapter number 8. So for example, there are various expressions for this delta, which is the thickness of the boundary layer, and C, which is the coefficient of friction. But let's focus on Nusselt number expressions for the time being. So Nusselt number expression is 0.332 Reynolds half Prandtl 1/3 if, which is 7-23 of this particular book, which would be applicable when we are considering the flow over a flat plate and the flow is laminar. And this is the expression for This is the expression for local Nusselt number because it says NUX. So we have got X in the suffix of Nusselt number. So therefore it would be local Nusselt number. And then it says TF. TF means that the properties would be evaluated at TF. So the properties such as Prandtl number, such as viscosity, such as thermal conductivity, so all those properties would be evaluated at TF, means film temperature, which is the average temperature of Ts and T infinity. So you may write TF is equal to Ts plus T infinity over 2, and this is applicable if Prandtl number is greater than or equal to 0.6. Then this is NUX bar. So that is for the laminar flow over a flat plate, and it gives us the average value of the Nusselt number over the entire plate. And again the properties would be evaluated at mean film temperature. Similarly, this expression of Nusselt number would be used for the flow over a flat plate when the flow is laminar, and it would give a local Nusselt number. The properties would be evaluated at the film temperature, and Prandtl number is much less than 0.05, because if you recall, that was the condition for liquid metals, for the flow of liquid metals. Now moving onwards, this is the thickness of the turbulent boundary layer. This is the thickness of the turbulent boundary layer. This expression of Nusselt number would be used when the flow is taking place over a flat plate and the flow is found to be turbulent, and it will give us a local Nusselt number because it says NUX and it does not have a bar on Nusselt number. The properties will be evaluated at TF, film temperature, and Reynolds number if the Reynolds number is less than 1 exponent 8. So means that the flow is turbulent, because for flat plate it is 2300. The critical Reynolds number is 2300. No, sorry. For the flow over a flat plate, critical Reynolds number is 5 exponent 5. 5 exponent 5. 2300 is for the flow through a inside a cylindrical shell. Then NUL bar, right? So it is the average Nusselt number, which would be given as per this expression. If you recall, I had shown you this expression, and in one of the similar expressions this was written as A. So I had told you that how that A is calculated, and it came out to be 871. So this equation is used for the flow over a flat plate when the flow is mixed, right? Mixed boundary condition, laminar boundary layer and turbulent boundary layer as well. It will give us the average value, right? And properties will be evaluated at TF, mean film temperature, and critical Reynolds number is 5 exponent 5, etc., etc. Similarly, this expression of Nusselt number C Reynolds to the power m Prandtl 1/3 will be used for flow over a cylinder, and it will give us average value of the Nusselt number, and the properties will be evaluated at the film temperature if the Reynolds number is in this range. And in fact it refers to table 7-2, and if we go to table 7-2, you would recall that 7-2 was a table where we were given various values of C and M, and those values were varying with Reynolds number. Similarly, this Nusselt number, this expression of Nusselt number will be used if the flow is taking place over a cylinder and if the Reynolds number is less than 1 exponent 6 and Prandtl number is between 0.7 and 500. So you can see there are a lot of expressions for Nusselt number. For example, this one, right? So this one can also be used for the flow over a cylinder. This one will be used for the flow over a sphere, and it will give us average value of the Nusselt number. And the properties will not be evaluated at TF, rather they will be evaluated at T infinity. And similarly, we have this expression of Nusselt number, which can be used in the case of a falling drop, and it will give us average value of the Nusselt number. So there are other expressions for Nusselt number as well, but of course over here are those expressions that are more commonly used. So that is the table at the very end of this chapter, external flow, in which are listed all the expressions of Nusselt number along with other expressions as well. So we would not be going over this impinging jet. However, of course, we can make use of this expression to find out the thickness of the velocity boundary layer, or this expression to find out the thickness of the boundary layer if the flow is turbulent as per the flow conditions. So that is a table that I was talking about for long while we were going over various expressions of Nusselt number in the material of this chapter.